Hey everyone. So over the next couple of videos, we're going to be taking a look at different families of organic compounds and more specifically the various reactions that we can do with them. So just briefly, here is a look at all of the different functional groups. So we've gone through the naming of these, but now we have to going to look at their particular reactions. Okay, I'm not going to spend time going through this table, but you can see they have the class, what we call the functional group, the suffix we use when naming, the general formulas, and an example of each one. So here are some of our general carbon, hydrogen, our hydrocarbons, as well as our oxygen-containing compounds. Um, Feel free to pause and copy down this table. It would be very beneficial to have as we go through the rest of this chapter to refer back to. And here are our esters, ethers, and our nitrogen containing compounds, as well as their suffixes, an example, and the general formulas for each. Okay, so the first family of organic compounds we're going to jump into and examine in detail is, of course, the alkanes. Okay, now, alkanes, they're there's not many things we're going to examine with them. They don't do a whole lot in terms of what we're going to study. So alkanes are relatively unreactive for two main reasons. Here's a change, just so you remember what the alkanes are. Here's our first four in our homologous series of straight chain alkanes, methane through butane. So they're relatively unreactive. The first reason is because they are nonpolar. We'll come across this more when we get into more specific reactions, but uh, anything that's nonpolar is generally not susceptible to attacks by most common reactants. Okay, so we can't really get things to be attracted to and to attack the alkanes. Secondly, is the carbon-carbon and carbon-hydrogen bonds are actually very strong bonds and require quite a bit of energy to break. You can see their bond enthalpies there in brackets. So for these reasons, alkanes don't undergo a lot of reactions, but there are two in particular that we're going to look at. The first one is combustion. So we've already studied combustion a lot during our previous units, but we take an alkane plus oxygen and it produces carbon dioxide and water. Say for an example, we can take methane and take some oxygen. We have to, so combustion is a spontaneous process, but if we want it to happen in a time efficient manner, we do have to add that little spark for the activation energy. Once that's added, though, combustion will continue to go and self-propel itself. So we have methane and oxygen, and it produces carbon dioxide and water. We can also have incomplete combustion. So incomplete combustion of an alkane takes place when we have limiting amounts of oxygen. Okay, so complete combustion assumes we have a significant amount more oxygen than we do the alkane. Incomplete, we have a very limited amount of oxygen. Okay, in incomplete combustion, we get products of carbon, carbon monoxide, carbon dioxide, and water. And these amounts vary depending on the amount of oxygen we have present. Okay, this is why, for example, it's not good to say barbecue inside your house or cook inside a tent if you're camping. Okay, because generally these processes produce incomplete combustion. Okay, anytime you are combusting something, you see that black char being formed on it, that's the pure carbon. But the dangerous thing about incomplete combustion is the carbon monoxide that's produced because we can't detect that without using a carbon monoxide detector. We can't smell it or anything like that, but it is quite dangerous to humans and you can have carbon monoxide poisoning. So that's combustion, the first reaction. Second reaction we're going to study is substitution. Okay, which we substitution reactions is the process of replacing one thing on a compound with something else. So in this case, we're going to replace a hydrogen with a halogen. So replace a hydrogen with chlorine, for example, and we call this halogenation because we're halogenating the alkane. So alkanes will undergo halogenation if they're reacted with a halide or a halogen ion in the presence of UV light. Or sorry, not I shouldn't say a halogen ion, I should say a halogen radical in this case, which we'll see in a moment. For example, if we take ethane and react it with chlorine gas, if we expose this to UV light, we get chloroethane and hydrogen chloride gas. This process happens through free radical substitution. And we're going to take a look at that in more detail. So what is a radical first? Radicals are species with unpaired electrons. So we've talked all this time through all of your chemistry learnings and previous grades as well. You've always learned that electrons come in pairs. Well, not the case with radicals, and this is what makes them so reactive. Okay, so radicals, you may have heard of antioxidants, so something that you're supposed to get in your diet, and they say antioxidants protect from cancer and all these things. Well, radicals, what antioxidants actually do is reduce the number of radicals in our body, supposedly. So radicals, being so reactive, literally react with anything they can come in contact with. They react with our DNA, causing mutations. Radicals are what reacts with ozone, causing the depletion of the ozone layer. Okay, so anything they can get that electron to bond with, they will go to it. Halogens form radicals when hit by UV light of the right frequency. So for example, if we have a chlorine. So Cl2, it's a diatomic element. We have chlorine, and we expose chlorine to UV light, ultraviolet radiation. Okay, what happens is this chlorine bond splits. And it splits. One electron goes to one chlorine, and the other electron goes to the other chlorine. Now we draw what we call fishhook arrows to represent the movement of just one electron. So it's a single-sided arrow. And this produces two chlorine radicals, which we draw with a dot after the chlorine. So it's not charged, we're not making an ion, but each one has now an unpaired electron. So the dot after the chlorine represents that unpaired electron and tells us that we have a radical. Okay, and this process of the bond breaking is called homolytic fission. So this is when the bond breaks equally with one electron going to each chlorine. Previous to this, what we've studied was heterolytic fission, which is where we have both electrons going to one substance when a bond breaks. Now we have homolytic fission instead of heterolytic fission. After we form this, we start the process of free radical substitution to substitute our alkane to form a halogenoalkane. So the reaction mechanism for this comes in 3 steps. Step 1 is initiation. We need that formation of the radical. Remember, an alkane is a very unreactive species, but a free radical is a very reactive species. So first we need the formation of the radical. Okay, we get this by exposing a halogen to UV light. It undergoes homolytic fission. Secondly, we have what we call propagation. So this is where a radical starts to make more radicals. Okay, so these steps feed each other and the radicals continue. So what happens, let's say we're using ethane as an example of what we're substituting. So a chlorine reacts with ethane. Okay, and in the process makes C2H5 radical. So it makes an ethane radical and HCl. That ethane radical can then react with another chlorine, creating our chloroethane as well as a chlorine radical. Okay, that chlorine radical, this propagation then continues because this chlorine radical then starts the whole process over, reacting with ethane, and so on, and it keeps happening in a cycle. Okay, so we create more and more radicals very rapidly due to the fact they're so reactive. Lastly, we have termination. So any 2 radicals can combine to terminate in the reaction. At the beginning, the concentration of radicals is going to be very, very low, so they're not really going to find each other to react with each other. They're going to find everything else first. So the propagation steps continue until we build up the amount of radicals that we have, and then they start finding each other. And basically termination, we take any 2 different radicals and combine them. So we could have the combination of 2 chlorine radicals to make chlorine, a chlorine radical and an ethane radical to make chloroethane, or 2 ethane radicals to make butane. Okay, and these are 3 different terminations that we can have. So a single radical can cause thousands of cycles of propagation. This is why, for example, chlorofluorocarbons being released into the ozone layer, this is why this is so dangerous and so important that these have been stopped being used, because just a couple of those can cause thousands and thousands of ozone molecules to be destroyed by just a handful of these chlorofluorocarbons getting into the atmosphere. Okay, so they are quite dangerous. And same with our body. Getting them into our body, hence why antioxidants are important, can cause thousands of propagation steps, destroying different DNA structures or other things in our body before they start to terminate themselves. Okay, this same mechanism, so this free radical substitution, 3 steps: initiation, propagation, termination. This applies to any halogen. So we don't have to use chlorine, and we can replace it with bromine or fluorine or iodine. Any of them apply, and we can react them with any alkane to make a halogenoalkane. So that's the purpose of this, is to change an alkane to a halogenoalkane. Okay, and the alkane itself can be substituted multiple times. So we can essentially replace each hydrogen in an alkane with a chlorine by just putting it through this mechanism over and over and over. Okay, and that is, so yeah, these are the 2 reactions that you have to know for alkanes. So combustion was the first, and free radical substitution is the second. One final note is that we can actually test for this free radical substitution in the lab. So if we take 2 test tubes of hexane, okay, so just an alkane, and we add about a milliliter of, or 1 centimeter cubed of bromine water to each, stopper them and shake them up. So bromine water is an orange color. It had just water with dissolved bromine in it. So when you shake it, both of them will be orange due to the bromine water. But if you leave one test tube in the classroom and take the other test tube outside and shake it in direct sunlight, what happens is that the bromine will initiate the free radical substitution process. So the bromine will break apart into free radicals and react with the hexane in the tube. Because the bromine is reacting, the orange color of the water disappears as we form bromohexane, whereas the one in the classroom, the orange color will remain because the bromine does not start or does not undergo that homolytic fission due to not being exposed to ultraviolet light.